I'm Katie Micklejohn. I coordinate the High Plains Grasslands Alliance. We are a grassroots nonprofit organization based out of the Las Vegas, Watrous region. And we are going to hear today from Kate Ziegler about geologic mapping, how it works, and why we're also interested in it, what it can do for you as landowners in terms of the information you can gain and the decisions you can make. This project or this webinar is supported by the Western SARE. And many of you know the High Plains Grasslands Alliance and New Mexico State collectively received a Western SARE grant 3 years ago. We're in the final year this year, and just wrapping up some of the work we've done through that process. So this work has been supported partly through that grant. And I will hand it over to Kate.
All right. Amy, is there anything else we need to say on behalf of Western SARE before I get going? So hello to everybody. Just in case there's anybody here that doesn't know who I am. Kate Ziegler, free range geologist, owner and senior geologist at Ziegler Geologic Consulting. And I think just about all of you have bumped into some of my loose in your pastures. So one of the things that I want to do today is a lot of you have heard me talk about geologic mapping and why we do it. And so I want to actually share some of the nuts and bolts of how it works and talk about what we can collectively gain from having that information in terms of thinking about our groundwater resources. So just for some quick background on how I came to be a part of all the stuff that's going on. I started in December of 2010 working with the Northeastern Soil and Water Conservation District, which is Union County up around Clayton, doing groundwater resource management with them. And so they started in December 2010, and Mora Wagon Mound Soil and Water Conservation District, they jumped on board in 2014, and we now have Mesa and Ute Creek Soil and Water Conservation Districts, Colfax and Southwest Clay, all involved in monitoring their groundwater. And so part of the data sets that we gather that I think we don't spend a lot of time with when we all talk about it is, you know, we talk about our water level measurements and what the water tables are doing from year to year. But the bigger picture that my team's trying to get at is the context of why do different wells act the way that they do? And why do we have different groundwater resources in some places and not in others? So for example, why can we farm around Sedan or Clayton, but we can't farm around Mosquero or Roy? And we're going to see that agricultural production can be directly tied to the geology under the ground. But my team has to understand it before we can figure out why this is all working the way that it does. So I'm going to go ahead and jump into the PowerPoint. You can keep questions flowing in the chat. I'll try to keep an eye on that as I'm going. And I'll stop. There are a couple of places where I'm going to stop and ask to see if anybody has any questions so we can kind of I don't like making folks hold your question in your brain until we get to the very end, and then you can't remember what you were going to ask. And I can't remember what slide I was on. So I'm going to go ahead and see if I can do this share screen. All right. So if this will get out of my way. Okay. All right, can everybody see the PowerPoint? Okay. Nods, sure. Okay, I'm gonna also pin myself per Amy's suggestion so that I can do some hands. Geologists, when we teach, we're very arm wavy. We do a lot of arm waving, so we're gonna do a lot of arm waving today. All right, so we're going to talk a little bit about these maps that my team makes. And my whole team is listed off on the side. So now you have names, but you don't have faces. So you still don't know who those crazy people are out in your pasture. So why do we make geologic maps? If I were to show you a geologic map, it would very much look like someone spilled a whole bunch of different colored paints on a map of New Mexico. And there would be reds and greens and purples and browns. And so when we're looking at a geologic map, it's telling us about the location in any given part of the world of different types of rocks and different ages of rocks. And something that's really cool about geologic maps is the colors are the same no matter where on the planet you're mapping. So we use the same colors everywhere in the world to talk about the same age and the same type of rock. So for example, if you look at a map and you see yellow, even if it's a map somewhere in China or in Europe or in Africa, it's telling you that those are young sediments. They're yellow in color. Reds are volcanics. Browns are Precambrian granite. And so any geologist can read another geologist's map, no matter where that map is made. We're also going to show you how those rock layers are oriented in space. So I have my handy dandy visual here. This is a stack of construction paper that we're going to pretend is rock layers. Thank you to the Truth or Consequences Walmart. They got great stuff in Walmarts. So we want to think about whether or not our rock layers are all nice and flat lying. This is simple. Or are they tilted? Or are they folded? And so on a geologic map, information about how rocks are oriented under the ground is incorporated into that map. We also have things like faults, so where rocks are broken. So when we talk about the San Andreas Fault Zone, that would be depicted on maps through California, where all our volcanoes are. We have all those on there. And we're going to look at some different geologic maps from around New Mexico that are going to show some of these different features. So the map is just a 2D. It's like you're looking down on the surface of the planet. And if you could strip all the vegetation off, these are the different rocks you would see looking straight down. A cross section, which always goes with every geologic map, is as though I took a bulldozer and I made a giant slice through the ground so that you can see down into the earth, and I'm projecting where I think all those rock units are going under the ground and what I think they're doing. So I think some of you can already start to see that when we think about, oh, my well's going dry, where should I drill a new well? My ability to project where I think different rock units are under the ground is going to help us think about tackling ideas of where might there be other water resources. Do we want to go deeper? Do we want to go sideways? Do we want to go uphill, downhill, closer to the stream, away from the stream? All of that information that I talk about is coming from these maps. So how do we make a geologic map? This is a crash course. This is all of 4 years of geology I'm about to cram into your brains in hopefully about an hour. So hold on tight. So the image here, this is a topographic map from down in the Permian Basin. This is a quadrangle. It's called the Singer Lake Quadrangle. It's located west of Artesia. And this is a little more old school. This is how I map. Some of my staff, they have their tablets because they're younger than I am and they know how to do technology and I don't. So they run around with their little tablets and do all this digitally. But basically, if you see me out there in your pasture, I'm going to be running around with a topographic map, a paper map that shows your landscape. And you'll see there's all kinds of lines and little symbols drawn on this map. So what I'm doing is I've walked around all over this quadrangle. Okay, a quadrangle is 7.5 miles by 8 miles. So we're about 56 square miles on a quadrangle, and we're going to walk all over it. And everywhere we see an outcrop of rock, we're going to go to it, and we're going to take a Brunton Compass, which is that super fancy compass down in the right-hand corner, and we're going to use that to determine whether or not the rocks are flat lying, or are they tilted, or are they folded? What are they doing? So we're going to take measurements. We're going to plot it with GPS so that each of my data points on the map are as precise as I can get them. And because I can see rocks wherever I've stopped, I'm going to look at them and I'm going to describe them. Is it sandstone? Is it limestone? Is it granite? Is it shale? So if you think about when I talk to you all about water quality, okay, that understanding of the chemicals that are in your water is coming from looking at the rocks and understanding the minerals that are in the rocks that are giving us water quality differences. So we're looking at the rocks, we're measuring the rocks. Sometimes you're going to see us out there wailing away on them with a rock hammer because we're trying to take a sample, which is usually fairly entertaining to watch because it never goes well. And basically what we're going to do on this topographic map is we're going to draw outlines of different rock types and different ages of rocks. And we're also going to include information about whether or not they're tilted, are they flat lying, are they folded, are there lava flows, is there a volcanic vent here? All that gets drawn on that paper map and included in notes in our field book. And then this gets scanned in, and our GIS team takes that scan and creates the nice, colorful, pretty digital version of this. And then from the data that's on this map, I'm going to create that cross section, that profile under the ground, to try to interpret what's going on beneath our feet. All right, come on. Uh-oh. Okay, sorry. Okay, some concepts to keep in mind when you're making a geologic map. So I'm not going to go into all the coursework that geologists are required to have before they even let us have a topo map and send us out in the field. When you learn geologic mapping, and it's in a class called structural geology, it's something that's done your senior year. And so you've had 3 to 4 years of other geologic classes before they allow you to get to this stage. And so what we're doing is we're taking 3-dimensional and 4-dimensional concepts and switching them into a 2D format, or taking a 2D map and switching it into a 4-dimensional concept. So there's a lot we have to keep in mind. Some ideas that are just, I tell all my staff when we start mapping, know your rock units. Okay, if I give you 2 pieces of sandstone, could you tell a Cretaceous Dakota Sandstone from the Permian Glorieta Sandstone? If you can't, you're going to have a problem, because you're going to walk out and find an outcrop of sandstone. You're not going to know which sandstone you're on. And we'll see in a minute when we look at some of these geologic maps that it makes a real difference if you don't know which rock you're on and how old it is. So that ties into the next idea, is know how old your rock units are. Okay, we're going to talk about the 3 principles that are listed right below that in just a minute. But basically, if you don't know the ages of the rocks you're looking at, you may not realize that the rock units are not in the order they should be in, and that there has been some catastrophic event that has affected that landscape, and that's going to booger up your interpretation of what's going on below the ground. Occam's razor is your friend. Don't make it overly complicated. I'm terrible at this. My staff got on me all the time about this. It does not need to be complicated. It's okay to be confused. It's okay to go back to the same place 8 times. It's okay to go get another one of us and go back to it 8 times and argue. Joshua and Keisha, if you ever watched us while we were out there mapping, you probably saw Ethan and I doing this at each other on an outcrop. And yeah, that was us arguing because we didn't know what the hell we were looking at. We're going to talk about some geologic events that can change the order and the arrangement of the rocks. And so we're going to talk about faulting and folding, but we're also going to talk about fossil topography. And that's where ancient riverbeds cut down through existing rock layers, and then younger rock units filled in on that landscape, and how volcanoes erupt into the middle of all this and make it even more complicated. So there's a whole bunch of information that we got to be holding in our head as we do this. All right. So if there's anything you take away from what we talk about tonight, these are probably the 3 most critical things. For any given sequence of rocks, if nothing else has happened to those rocks, we haven't built mountains, we haven't stuck volcanoes through it, we haven't done anything else, whatever layer is at the bottom of a stacked sequence of rocks has to be the oldest. It has to have been formed first so that you could stack younger layers on top of it. Okay. So another example that we use is if you read the news back when we read paper newspapers. Okay, this analogy doesn't really hold anymore, but if you read the newspaper every day and you put it down next to your chair in the morning and you never pick those newspapers up, the first newspaper you read would be at the bottom of the stack, and the one you just read today would be on the top of the stack. Okay. So if you know the ages of your rock units and you see a younger rock underneath an older rock, then you know that something has happened to that sequence of rocks since it was formed. And you need to think about what happened to it and why. This folds in with what's called the principle of original horizontality. And this is that sedimentary rocks, which are formed by oceans and rivers and streams and lakes, and also lava flows, that they originally formed flat lying. So in the picture above, you can see this young man is standing next to layered rocks that are tilted on their side. Okay, so something has happened since those rocks were deposited flat that has tilted them. And now we need to think about, why are they no longer flat lying? Okay. And so if we're thinking about how rocks can be deformed, this is going to have implications for where groundwater resources are when we project things under the ground. And then the third one is the principle of cross-cutting relationships. And that is that if you have like a fault where rocks have broken, the rocks had to have formed first before we could break them and have that fault shown. Okay. So faults are always younger than everything that they cut across. In Northeast New Mexico, we don't have a whole lot of faults. We do in the Rocky Mountain Front Range. So in the Sangre de Cristos, we see a lot of faults there that are related to the building of that mountain chain. And all those faults have to be younger than the rocks that they cut. Okay. So I'm going to stop here for just a second. Does anybody have any questions? And Katie, I can't see the chat thing, so if you can help me monitor that, that would be awesome.
I'll keep an eye on it.
Okay, are we good to go?
I think so.
Katie, I have a question. This is Will.
Yes.
Do you, on your travels in the Turkeys, you were mentioning some of the Fort Union work.
Yeah.
Do you find much faulting associated with that igneous intrusion below?
We do. Actually, in the maps that we're working on, that we're finalizing, we actually have, well, we have both a beautiful ring fracture that's because of that punching upward of that igneous intrusion, as well as some basin and range faults that cross-cut that whole thing. So yeah, it was really neat to see a beautiful ring fracture. It goes right around the Central Valley. It's really neat, really, really cool. And this is something that as we finalize those maps and as Fort Union feels like they would like to showcase what we've learned from them, we can potentially talk further about that in another meeting. Did that answer your question, Will?
Yes, thank you.
Yeah.
It's just such a cool area and we see it every day.
Yeah, it really is. There's in mapping in there, we saw some really cool stuff we didn't expect to see. And like I was just saying, I'm sure that the whole family saw Ethan and I out there arguing strenuously with each other in many places because we were really confused by several things that we saw out there. It's really cool. So, all right, other questions? All right, so now I'm going to get into a few of and most of these are going to be related to how the rock units are oriented in space. Okay, so the first thing, this is why we run around with those fancy compasses. When we measure how much a rock unit is tilted and in what direction, that measurement is called a strike and dip. And I usually explain these a little bit backwards because for me, it's easier for me to understand dip before I understand strike. But if you look at the figure here, we have a tilted layer of sedimentary rocks. And they're dipping at 25 degrees below horizontal. So that's the angle of dip. 25 degrees is actually pretty dang steep. You would slip and fall and face plant down this thing. 25 is actually quite steep. And in this case, if you look at your little north arrow, these, and actually I gotta move my little thing because it's over all of my images. Okay, so you can see we've got a little north arrow there, okay? So these beds are dipping off to the southeast, okay, at 25 degrees. So the dip and the dip direction are the amount of dip below the surface, okay? So I'm sure all of y'all are already thinking, let's think about that sandstone bed that's right below the limestone. If it's dipping at 25 degrees down, we can project where that sandstone might be under the ground. And if we think it's a good aquifer unit, we need to think about that 25 degree dip to the southeast to figure out where that aquifer might be further away from our outcrop. Now the strike is always perpendicular to the dip direction. So in this case, we have a strike that's going to be northeast southwest. And the strike is simply the intersection of a horizontal plane with those dipping beds. Okay, that's all that is. So when we run around with that big fancy compass, we're able to put it alongside the rock outcrop. It has two different level bubble systems in it so that we can measure the strike, and then we can flip the compass on its side and we can measure with an inclinometer how much it's dipping and in what direction. And so when you see this funny little line with a little tick and a little number on it on a geologic map, it's telling you the amount and direction of the dip of different rock units. Okay, so this is a super critical piece of information. Now, let's talk a little bit about rock deformation. And strike and dip that measurement often helps you see what can be very subtle structures that you might not otherwise notice. And especially out on the plains where we're dealing with a lot of grass cover, we're dealing with a lot of soil on top of things, even if it's not a terribly well-developed soil. Sometimes we're having to look at the rocks in a little creek bottom and then go to the next creek and look at those rocks in that creek bottom. And we have to interpret the strike and dips between two outcrops or two creeks to figure out what's going on between them. So when we squish rocks, when we're compressing them, if they're squishable enough, they're just going to fold. They're not going to want to break. So we're not going to get San Andreas Fault or any of that fun stuff. We're just going to get nice little folds. The Turkey Mountains are a good example of a fold. They're folded because something punched up from the bottom and forced them to fold in a dome, but they're a beautiful example of what we would call an anticline. An anticline is just an upfold. So if we take our fun layer cake, okay, and we're going to compress it or push it up with magma, we're going to form an anticline is our upfold, and the reverse, a syncline, is our downfold, okay? Now, if you notice on that lower figure, and I'm going to use my mouse cursor to try to highlight some things, this is as though we took this upper image here, and we're looking flat down on it, okay? So where we have an upfold, another way to think about dip is, I'm going to make my anticline again. Here's my anticline. If I drip water on the top of my fold, okay, water is going to want to roll off either side of it. Your little dip tick marks are going to be in the direction that water is going to want to flow. So if you look below the axis of the anticline in that left figure, you'll see all the little strike and dips are facing away from each other. Water's going to want to roll away from the center of that fold. If we have the opposite case, water's going to want to run into the fold. And so our little tick marks down here are facing each other, okay? So the sign for a fold, for an anticline fold, is a line along the hinge of the fold with two arrows going away, just like the dips go away from each other. And a syncline is the opposite, where we have our hinge line and we have everything rolling into itself, okay? So the Turkey Mountains, though, are a little special. They're what we would actually further call a double plunging anticline. And I cannot do that with this stack of construction paper. But basically we have a fold that is then folded along its axis. Okay, so that the fold is there and the axis itself is also folded. Okay, so it's more like a dome. That'd be another way to think about it. Okay, faults. Okay, so rocks are either going to fold when they're compressed or when they're punched by igneous things, or they're going to break. And different kinds of rocks either fold or break. Okay, so more brittle rocks like sandstone, limestone, granite, volcanics, those are going to want to break. Mudstones, shales, coal beds, those are going to want to fold. And if you have mixed soft and hard stuff, you're going to get a mixture of both types of deformation. So I have another fun little Walmart artsy craftsy moment. Okay, I made a little outcrop. I don't know if y'all can see it. Okay, so we have three different kinds of faults here. When we have the same type of forces that make the Rocky Mountains, we're compressing, we're squishing things. Okay, so if I'm going to squish my hands together, okay, my fault blocks are going to rise one. Bleh. Okay, I'm going to back up a minute because that did not come out right. Okay, I'm going to compress my little index cards. As I compress them, one side is riding up over the other side. Notice how my hands are getting closer together as my fault is slipping. I am compressing, I am losing space, okay? These are called reverse faults. They're called reverse faults because if we have the opposite case happen, Where we're extending, notice how my hands are moving away from each other. Okay, the one side's dropping down, the other side is going up. We are opening space. For whatever reason back in the day, geologists decided that opening space is a normal fault, and therefore if you do the opposite and you compress it, it's a reverse fault. That's all. There's nothing spiffy to these names. So the third kind are strike slip. And those are, this is what the San Andreas Fault in California is. And this is where there's no up or down. It's just two blocks of rock moving past each other. Okay. And then we just define it on which way is it sliding. And that's a whole nother thing to worry about. So when we're up in the Front Range in the Sangre de Cristos, where we have compression, we are building mountains. Mountains are built when plates collide. And so we have an incredible amount of compressive stress. And so we're going to see folds, we're going to see reverse faults, and we're going to see something called a thrust fault. A thrust fault is just a reverse fault with a really shallow angle. That's all. When we get the opposite, when the crust relaxes, we're going to get extension and we're going to get normal faults. Now, because different rocks in different areas are going to fault at different rates, we're going to tend to see those strike slip faults occurring where we need to accommodate things moving at different rates. And so strike slip faults aren't immediately obvious. Some of my colleagues in the state survey feel like a lot of us don't recognize strike slip faults out here. For the most part in Northeast New Mexico, what we see are mostly normal faults that are related to what's called the basin and range extension that happened after the Rocky Mountains formed. So we compress the crust, we build the Rocky Mountains, and as that compressive event finally ends, that crust is going to relax, and as it relaxes, it's going to extend back out. And so we get this compression extension. All right, let's look at a geologic map. Real quick, before I go too much further, any questions on faults, folds, strikes, and dips? Fabulous, y'all are almost all the way to your junior geologist degrees. Okay, map symbols. Here's a geologic map. It really looks like a kindergartner got happy with a box of crayons. We've got these funny little amoeba looking things, okay? So again, the upper part, that geologic map, that's the upper 2/3 of this image, the different colors are telling you age and rock type. So again, yellows tend to be our youngest, soils, alluvium, landslides, all the young modern things that are on our land surface. Greens and blues are our Mesozoic rocks, so our Cretaceous, Jurassic, Triassic rocks. Darker blues and purples are Paleozoic rocks, even older, all sedimentary. When we get to browns, we're into really old granite, our Precambrian granite. When we have bright reds and pinks, those are volcanics, usually much younger. And so again, the color is telling you age and rock type. So as you get more used to looking at these maps, that information comes to you immediately when you look at them, okay? In this case, you're also going to notice, okay, so here's my little mouse cursor. I'm kind of in the center around this strike and dip with a 17 on it. You can see there's a whole bunch of little strike and dips all through here, okay? And notice where we have, and it's not perfect because of course the world is not perfect, but notice here our 17 is kind of sort of pointing in towards this 43 over here. And so we have chosen to depict that there is a syncline where the rock is folded in towards itself and water's going to run in to the center of that fold. And over here, because we have dips that are opposite each other, we're going to have an anticline, okay, where things are tilted away from each other. We also have these dark lines running through everything with a little ball on them. These are showing us where normal faults are. So if you look on our map legend, not only do we have the color and what type of rock it is, we have our strike and dip symbol, and they tell you that the black line with the little ball is a fault, and the ball is on the side that went down. So if we look, for example, at this little fault right here, on the north side, you'll see those rock units have dropped down. And if you were to walk to the south side, they will have seemed to have stepped up versus the other side, okay? So we also have our anticline and our syncline hinges. And then from this, we're going to pick a place on this map where we think it's going to give us the most information for whatever question we're trying to answer. And in this case, these folks are trying to answer, why do I have this funny little amoeba shape? And so they chose to draw their line of cross section right across the middle of the map. And down at the bottom here, this is these authors' interpretation. If they took a bulldozer and they made a giant slice through the map, right through that line, this is how, using those strike and dips and those fault symbols and the fold symbols, this is how they interpret the land underneath this map to look like. So we have a big old anticline that rolls into a syncline that rolls into another anticline. Okay. So there's a lot of information just on this little tiny map. This map is from an area called San Ysidro in central New Mexico. This is a classic anticline syncline set that we take a lot of university students to for their very first mapping exercise. And you can stand up there and you can actually see the folds when you're standing down here by where the road is. Okay, I'm going to pause again. Are there any questions on this first go through a geologic map? All right, let's move on. Okay, so now I'm going to start getting, I'm going to bounce a little bit back and forth between the geologic units in Mora and Harding County, which is a study area that was funded by this Western SARE grant and is where my team has been working for many years now. We're going to talk about the geologic units in Mora and Harding County and how they relate to aquifers and how we think about them in terms of their groundwater characteristics. And then we're going to shift gears to look at a couple maps that are publicly available maps from a couple different places in New Mexico, so that y'all can see how we would apply the concepts we're going to talk about right now. So what we just talked about, plus what we're going to talk about now, to think about what a geologic map is telling you about where your groundwater resources may be. So when we look at the geologic units of Mora and Harding counties, any good geologist is always going to put their rock units in time order. So if I list them in bullet form like this, I'm always going to have the youngest at the top and the oldest at the bottom. Principle of superposition rules the day for every geologist ever out there. So if we were to dig down through the ground, these are all the rock units that y'all would run into if we could dig that far down. In some places, it's going to be several thousand feet to get through all of this. But we're going to start with all our modern stuff, river deposits, the aeolian sheet sand that is currently remobilizing itself outside of Truth or Consequences right now. I'm watching it go by. It's doing a lovely job of depositing. Landslides, talus, colluvium, all that young stuff. The surface that is active right now. And then we're going to get into what's called the Ocate volcanic field. So Wagon Mound, all the little cinder cones and volcanic vents that you see out towards Roy and Mosquero that go all the way up above Ocate, all those little lava flows that are all over that landscape. These are all part of a big group of small volcanoes that's called the Ocate volcanic field. To the north, there's also the Raton-Clayton volcanic field that includes the perfect little cinder cone of Capulin. These range, the Ocate volcanic field is generally older. It's in the 8 to 6 million year old range. When you get up to Capulin, things get much younger up there. But for where we are in Mora and Harding County, we're looking at 6 to 8 million year old flows. I just realized I left the Ogallala out of this. The Ogallala Formation is around in Mora and Harding counties. We hear a lot about it as a big aquifer out on the high plains. Where we are in Mora and Harding counties, it's very thin. It's in tiny little buckets that basically aren't big enough to act as an aquifer. So I tend to sometimes forget it because it's not as big of a feature on our part of the landscape as it is out in Union County or out into Texas, Oklahoma, Kansas, Nebraska. But we can't forget the Ogallala. And then this kind of gets at the point that Will brought up earlier in talking about the Turkey Mountains. There's an older igneous complex buried in the heart of the Turkey Mountains that would be Oligocene in age. So it's older than the Ogallala, but it's younger than all the Cretaceous rocks. And that's sort of its own special little story. And then we go through a whole series of Cretaceous rocks, the gray shales that you'll see when you drive up to Raton. We go through all of those, shale and limestone, They all have their names. I'm just throwing a couple of them out here, the Greenhorn Limestone and the Granero Shale. There's a whole bunch more of them as you go up to Raton. And then we have the Dakota Sandstone. This is what makes the hogback around the Turkey Mountains. This is what makes the caprock for the Canadian River Escarpment, for the dry Cimarron. When you get up towards Raton, a lot of the cliffs there are capped with the Dakota Sandstone. It's a big player in the landscape out here, and it's also one of our primary aquifers in Northeast New Mexico. Below that, we have the Jurassic Morrison Formation, which is a mix of mud and sand. We'll talk about that later. The Exeter Sandstone, I have in parentheses Entrada Sandstone, because another fun thing geologists do is we fight about the names of rocks all the time. And some people call it the Entrada and some people call it the Exeter. Anyway, below that we have the red beds, and then we have the Glorieta Sandstone, we have the Yeso, and we have the Sangre de Cristo Formation. The Glorieta and Yeso are exposed in the Turkey Mountains just because that has domed up so much that we did bring much older rocks up to the surface. The Sangre de Cristo Formation we only see over by Ocate, where it's been exposed in the mountain building of the Sangre de Cristo range, which is what it's named for. All right. So this is just taking what we just talked about, but putting it in more in a visual format. And so again, on the right-hand side, if you could dig down, if you could create a giant borehole and we could put an elevator in it, and we could just zoom down 4,000 feet down into the ground, this is what you would see as you went through. Like if we did this right at Wagon Mount, this is basically what you would see. We would go through the volcanics, some thin little bits of Ogallala, our Cretaceous rocks, and then we get into our Dakota Sandstone and so on down. The thing to watch on this figure is everywhere that one of my little boxes sticks further out, like the Dakota Sandstone, the Glorieta Sandstone, the Exeter. These are units that are sandstone or limestone. So they're going to be porous and permeable enough to be an aquifer. And everywhere that our rock units are compressed, these are mudstones and shales. These are not going to be good for water bearing. They're not permeable enough to give water. So this is giving you sort of a visual of good aquifer, bad aquifer as we go down in our little elevator. And then the central diagram here is just for the time nerds in the audience who want to see the ages of the rocks that we hold in Northeast New Mexico. And this is a whole nother discussion, but you'll notice we're missing a lot of time in Northeast New Mexico. There's a lot of the geologic time scale that's not preserved here. We're missing a lot of the early, right after the end of the dinosaurs. We're missing that whole chunk of time when mammals evolve and get big and specialized. We're missing the whole first half of the history of life on this planet is not preserved here. And it's for a lot of different reasons. But this is just to show you that it's not all the same everywhere. And we are frequently missing a big part of the story. And that's part of what we're trying to figure out. All right. So now if we think about the rock units, I'm just going to hone in on the aquifer units. So I'm going to ignore the gray shales, except I'm going to ignore the gray shales and some of the other rock units that are not good aquifers. Phoenix. So our aquifer unit, the volume of water that it can give you, its chemistry, and TDS is total dissolved solids. That's just a quick and dirty way of thinking about how gross your water is, okay? So high total dissolved solids, ick. Low total dissolved solids, you can go and fill your cup at your well and drink it, and it tastes great. pH, and then can that aquifer recharge? Because this is a big question that we all have, and this is something that we need to be thinking about moving forward. So I'm just going to touch on a couple of these. The Ogallala is not really present here, but over to the east, that can be high volume. There are wells in Texas that used to give 1,500, 1,800, 2,000 gallons a minute. Now most of those only run 300 gallons a minute, which still for most of us is amazing. The Dakota by comparison never really gives more than 5 to 8 gallons per minute, okay? So here's a good one. If we look at the Greenhorn limestone, low volume, 2 to 3 gallons a minute. high total dissolved solids. The water is frequently gray when it comes out of the well. You can smell the sulfur in it. It tastes awful. Cattle seem to love it. Whatever, good for them. Because it has a lot of gypsum in it, it has high sulfate. And so this can become a problem if we have evaporation of greenhorn, of water from greenhorn reservoirs, because as that water evaporates and the sulfate concentration increases, we can end up with bovine polioencephalitis. So something to keep in mind. Because it's a limestone, which is a calcium carbonate, the pH of water that comes from greenhorn limestone reservoirs is actually more on the basic side. So when we think about surface waters, we're always told we want our pH to always be right around 7, because it's hard for any aquatic animals or vegetation to survive when that pH shifts around. But if we look at groundwater, because it's been sitting in contact with these rock units with different minerals in them, we can actually see a really high range of pH values in groundwater, and that's totally normal. So for example, the Sangre de Cristo can have more acidic waters because it has a lot of granitic material in it, and granite contains minerals that are going to actually lower that pH and make it a little more acidic. And in terms of recharge, when we think about recharge, there's 2 questions we need to think about. How well cemented is that rock? Is it so tight that even if we just sat water on it for ages, it couldn't get down in it? If it's fractured, if it's faulted, if it's got lots of pore spaces, it can absorb that water. But the other question is, how deep below the ground is it? Okay, and we've talked about this concept before. We think about water migrating downward from the bottom of a stream. Groundwater works its way down through the subsurface about as fast as your fingernails grow. So if your aquifer, if your Dakota Sandstone is 100 feet below the ground, you can think about how long is it going to take for water to creep down all the way 100, 150 feet down. And it's frequently got to make its way through an impermeable shale that's going to make it even harder for that water to get down to it. So when we think about all our different aquifers out here, and there's a lot of them, okay, there's another concept we hear on the high plains is, there's oceans of water under there. It's all the Ogallala. When we start looking at the geology under Northeast New Mexico, all these aquifer units on this slide, they're all present. They're all at different depths because of faulting and folding and erosion. They all have different characteristics, and they're all going to behave differently. And so the geologic maps plus our understanding of the physical and chemical characteristics of the aquifers, this is a story that we're trying to pull together, okay? Any questions on these last couple slides?
Hi, yeah, I have a question. What was that you were mentioning about bovine spongiform encephalopathy?
Bovine polio encephalitis.
Polio. Okay. I'm sorry. I was like,
you're fine.
okay, because I'm currently writing a term paper about prion diseases, and I was like, wait, what? But I just misheard you. I'm sorry.
It's okay. It's related to high sulfate values. And so we're starting to see more and more of it, unfortunately, in Northeast New Mexico due to the aquifers diminishing. And so the salts are concentrating in that water, either as it's coming out of the well bore or as that water is allowed to sit and evaporate in dirt tanks or in drinkers. And there are a couple other rock units more over towards Clayton and in the Roy Mosquero area that are just naturally very high in gypsum. And so folks who have wells that penetrate that rock unit just have to be real cautious about watching for polioencephalitis in their herds.
Okay, thank you.
Yeah, I know nothing about prions. Okay, so now what we're going to do is we're going to run through a couple examples of geologic maps from parts of New Mexico. We're not using geologic maps from northeastern New Mexico in part because some of them are simply not ready for us to show yet, and others of them are proprietary. And so we're not at the point yet where we can publicly release some of them. But what I want to do is show you a couple open source geologic maps so that we can think about what are we seeing when we look at these maps. And then we're going to use the map legends to think about water quality And therefore, what are the aquifer units we might want to target? And then if we were to look at this geologic map and we were a rancher in that area and we're trying to decide where to drill a well, like a new well or a replacement well, where are we going to want to drill it if we have this data in our hands? And then we're also going to talk about some of the things we need to be careful with when you use a geologic map. Things like, did your geologist do their job right? Did we extrapolate those rock units under the ground the right way? I way overshot a cross section once and someone drilled a well and I was nowhere near where I was supposed to be because the rock units actually changed their angle under the ground, and with all the grass and soil cover, we couldn't see that. So we're going to talk about some of these caveats. Do the rock types change under the surface? Some units like the Morrison and the Dockham group, if you were to walk along an outcrop of them, you would literally walk from sandstone into mudstone, into sandstone, into limestone, into more mudstone. And so under the ground, what are these rock units doing? Do we have faults that we can't see on the surface? They just terminate somewhere under the ground, but they offset things enough that maybe a rock unit is higher or lower than we think it should be. And then how do volcanics create barriers to groundwater flow? All right, so, okay, here's our first geologic map. This is the Bull Gap Quadrangle. This is in the northern Tularosa Basin. So this is just south of the village of Carrizozo. We would have the Sacramento Mountains to the east. We would have the San Andres and Osceola Mountains to the west. White Sands Missile Range is right south of this. And what's the first thing that jumps out at your eye on this map? And y'all can unmute yourselves for the next few slides. What's the first big thing that pokes you in the eye when you look at this?
The volcanics.
That bright red right across the upper part of the map. That is the Carrizozo lava flow. One of the two youngest lava flows in New Mexico. It's a baby at 3,000 years old. And so that lava flow, that's telling us a little bit about the old landscape, right? Because lava likes, it's a fluid. It likes to flow to the lowest part of the landscape. So 3,500 years ago, that red is where the old watershed used to be. That's now much harder than everything around it. And so everything around it is weathering down. We're leaving the old bottom of the watershed now sitting up high. It's not terribly high out there, but it's getting there. And then we see a whole lot of very unexciting colors, grays and browns and blues and greens. And again, when we look at these, those yellows, and unfortunately the way this rendered, at least on my screen, the yellows are yucky yellow. They're like awful mustardy yellow. These are our young sheet sands, aeolian deposits, alluvial deposits. And then the blues and greens are Permian, Triassic, and Cretaceous sedimentary rocks that are uplifted along, like there's a ridge running right up the middle of this map. And there's a canyon in that that's called Bull Gap, and that's what it's named for. So on the right side here, we have the different rock units that we see on this map. Notice we've got at least a couple familiar faces here. We've got the Dakota Sandstone. The Manco Shale would be the same as some of the gray shales we see around Raton. It just gets a different name down here in southern New Mexico. We have the Yeso Formation. We saw that in our description of Northeast New Mexico rock types. And if we look at all these different rocks, okay, we have a variety of things here that could be an okay aquifer, a good aquifer. We've got some water quality problems. Okay, so in the alluvial sediments, those can make a fabulous aquifer, nice right along all your drainages, but there's a lot of gypsum out here. Okay, so we want to think, how much do I want to risk on gypsum rich water? For example, our Gallup sandstone here, that can be a good aquifer. It's got pretty good quality. Dakota Sandstone, again, pretty good aquifer. Artesia group, it has some sandstones in it that can make good aquifers, but it's got a lot of gypsum in it. San Andres Formation's got some limestone in it, can make a great aquifer, but it's got a lot of gypsum in it. So when we're looking at this map and we're thinking about, okay, I got to figure out where along in the southern part of this, I want to drill a new well. First thing I'm going to do is look at my map, look at where my ranch is, look at where my boundaries are, look at what are the rocks that are exposed in my little area. And right now we're going to focus just on the southern half of this map. And then you're going to go over the legend and you're going to look at all these different rock units and you're going to think, okay, it's a sandstone and I know it's going to be pretty good because it doesn't have a lot of weird minerals in it. And this is where having all the geologic background helps you to make these interpretations. So now what we're going to do, keeping all this in mind. Okay, here's that cross section. Let me bump up one slide real quick. Okay, see the black line right here? It's got cross section pointing to it. Okay, this is as though I sliced through the earth. Northwest to southeast. Okay, so here's all these tilted rock layers coming across that map. And what I want all of you to do is to look at these 4 locations. We have A over here on the northwest side, B, C, and D. I want y'all to consider if you had to pick a location for a new well, which one would you pick and what are the pros and cons for these different locations? Okay, so let's think about our rock units real quick. So we've got some igneous rocks up here on the bluff, Crevasse Canyon, which is sandstone with some shale, Gallop Sandstone. KT is part of the Mancos. This is a black shale. We've got our Dakota. Oh, I missed our Gallop. So Gallop, Mancos, Dakota, our Triassic Moen Copy, which are sandstones and siltstones. We have our Artesia group. We have some San Andres up here. We have our Yeso. And gosh, look at what these faults are doing. My goodness, we're moving stuff up, down, sideways, and everywhere. Okay, so we have Moen Copy here, side by side with much, much older Yeso, side by side with younger Artesia. So stuff's hopping and bopping under there. Got a little baby fault over here. Okay, some things to consider. How deep are you going to want to drill? Remembering that for every foot you drill, that's money. If your first target fails, is there something you think you could drill deeper to? And I hate this thing keeps moving around where I can't see anything. Water quality. Okay, are you going to want to take the risk of lower quality water just to get water? Okay, that is a viable thing to think about. If it's too deep to potentially recharge, and think about your infrastructure issues for where you're going to drill. Okay. So Amy, do we have the poll results?
It should have popped up. I don't think anybody's voted yet, or I'm not sure if anybody's voted, but if you guys will use that poll and just vote on what section you'd pick to drill your well in, that'd be great. It's all anonymous. It's okay if you're wrong.
No one's going to fail for what they picked.
That's right.
While y'all are thinking about it, there's an exercise we do with K-12 students where we have a box of sand and gravel, and it's a little valley of gravel with sand on either side. The sand's supposed to be the bad aquifer, and we cover it completely with paper, and we give each kid a straw, and they don't get to see what's in the box, but they have to choose where to drill their well. And it really drives home to them the stress of not knowing where the heck to put their straw because they can't see what's under the ground. And this is what most folks have been doing for the last 70 years since we learned how to drill wells, is effectively shooting blind and just hoping like heck that you can hit something, unless you're a witcher. Having just watched one of our construction guys totally witch a water main that the Water Utility Authority couldn't find. I ain't touching that one.
All right, so you have 5 more seconds to select which rock layer. Let's get a couple more.
Some of you are hedging your bets and not picking any of them. All right.
Kate, you should see the results now, I think.
Yeah, I did. Thank you. All right, so one person for A, couple people for B, no one likes C, and a bunch of you really like D. Okay, so thinking about A, I'm gonna pick on that one. We've got San Andreas limestone over Yeso. I'm gonna go ahead and roll up one slide. So hold this image in your mind. Okay, San Andreas and Yeso. San Andreas can be good because it's a fractured limestone, but we have to worry about that gypsum contribution. And if we drill down into the Yeso, it's also going to contribute gypsum. So thinking about, are you willing to take that risk? And sometimes that's all you've got, and that's what you've got to work with. But thinking about that trade-off between good water versus poor quality, okay? That is a viable option. You can supplement to deal with high sulfate, but it is something you would need to watch for, okay? B. Okay, some of you picked B. Does anybody want to jump in on what they think is good or bad about location B? Nobody wants to.
See the Dakota nearby.
Aha.
And it would be relatively shallow.
And there's a contact.
We like the Dakota. What's going on with the contact, Will?
Contacts can be conduits.
Yes, sir. Very good point. Okay, so what Will's talking about is where you have, I'm going to get my construction paper again, where we have changes between rock layers, that horizontal plane where two layers come in contact with each other. Frequently, that's a zone along which water will want to travel. Not always, but frequently, okay? In this case, I would note that the Moenkopi, which is below the Dakota, this can be a backup. It has sandstone and siltstone beds in it that if the Dakota starts to fail, you do have a slightly deeper option. It may not be as great, but you do have a backup plan at B. All right, does anybody want to jump in on why no one liked C? Poor C. Nobody likes C. What's wrong with C? I'm gonna start randomly calling on people. Willard.
It was the shale that I thought was not such a good thing.
Okay, so we have a pretty thick sequence of shale. What might be the only reason you might pick C? If we drill at C, if we go deep enough, okay? This would be if you had no other option. And this is where expense becomes an issue. But if you had no other option, but you had to drill right here, knowing that you're going to have to get through a couple 100 feet of shale before you can even get down into potential aquifer units. And knowing that the shale is going to be contributing gypsum to the water that's in that aquifer. Good. Everybody liked D. What made y'all happy about D? Five of you voted for it. Come on. Good Lord, y'all. I'd have to tell everybody to go get a beer and come back. Okay, Gallup. The Gallup Sandstone. What happens too if the Gallup does eventually go dry? It's going to suck because you're going to have to go probably about 1,000 feet down, but you do have a backup plan further down in the Dakota and the Moenkopi. It'd be awful, but you do have a big backup plan on this one if the Gallup Sandstone does not work out. Okay. So this is one way that we can use these maps, thinking about the tilt of those rock units and their different characteristics, thinking about our options, and also for wells that already exist. If we already had wells on this landscape, why do wells over here act differently than wells over here? Okay, it all comes down to these different rock units. All right, let's do one other one. This is ugly. Please don't
Wait,
tell.
which one did you pick, Katie? Kate?
So I would have gone for either B, because I have the Dakota Moenkopi combined, or I would have scooched just a little bit over here so I got a thicker sequence of the Gallup. Those would have been my choices. But that would be me just wanting to steer clear of dealing with quality issues over here at A. Having seen the effects that can have on a herd if you don't catch it in time, I would tend to have A be one of my last options just because of the quality issue. All right. This map, Lord, this will make your eyes bleed. The colors here, again, the pinks and the oranges and the reds, these are volcanics. The greens are all Cretaceous sandstones, limestones, and shales. And so each of these little mounds with a little asterisk on it, this is a little volcanic vent. And these are all these little lava flows that have all come out of all these little vents, and they've spilled out over this landscape. This is off the edge of Mount Taylor in western New Mexico, big volcanic complex. And so you can see this complicated relationship of all these lava flows flowing all over one another and flowing over these Cretaceous rocks. Same Cretaceous rocks we've been talking about this whole time, shales and sandstones, names that y'all know. And so one of the things that gets weird when we add volcanics into the picture, and the reason I added this is because of the Ocate volcanic field and the Raton-Clayton volcanic field. You not only have your magma chamber that's down there, that's providing the magma that's going to flow out on the surface and make these lava flows. That magma chamber is going to come up to the surface via a little conduit. Okay, so it's going to make these little volcanic necks when that landscape erodes down. But off that magma chamber, you can also get vertical walls of magma that travel along fractures. And they can form a wall that's effectively going to pool groundwater on the uphill side. And then sometimes that magma is going to creep out along the bedding planes that Will talked about, that contact between rock units. You'll get these zones of magma that cool and crystallize under the ground, and you can't see them. You have no idea they're there until you put a well through them. And so those are also going to create impermeable barriers. And another thing that happens is as that magma intrudes into these rocks and it's cooling, it's losing its heat to the rocks around it, and it's baking those rocks. And as it bakes them, it decreases their permeability and their porosity. There are a bunch of little tiny, when they're vertically oriented, we call them dikes. When they're horizontally oriented, we call them sills. And there's a whole bunch of little dikes all around the Turkey Mountains. Some of them are literally this wide, but they look like a little railroad track. And that's because as that magma came up and it heated the rock around it, and then that interior part erodes, you're left with these little walls of basically baked rock on either side. So here's our cross-section line. Notice the authors chose to put a little bend in it because they wanted to pick up several interesting features. Your cross-sections don't always have to be perfectly straight. Mostly we try to do that, but it doesn't always have to be that way. So here's our cross-section. That's pretty nice. Okay, most everybody's pretty flat lying. We've got a little tilting in some places here, but it's not much. We've got our both our conduits. So this is a conduit from a magma chamber that's much further down that has fed these flows up here. We have a dike right here. And then we have this god-awful mess over here on the southeast side, where we had magma try to erupt and it didn't quite make it all the way. So this is kind of like the Turkey Mountains, but much more dramatic, because as this popped up, it scrambled everything up above it. So you look at all the rock units above it and it's just a disaster in here. So if you're trying to pick how to place wells in the San Fidel Dome, man, you're going to have a heck of a time with that, because that is one jumbled up mess over there. Notice that this brown magma, I'm going to flip up a slide. Okay, that's down here. This is the San Fidel Dome down here. You can't see that magma. Okay, its position under there, this is interpreted. This was the geologists interpreting what they saw on the land surface to create that cross section. Okay. Now, one other interesting feature here, I mentioned that when you get the vertical intrusions of magma that form the dikes, if your rocks are tilted ever so slightly, your regional groundwater flow is going to want to be moving to zones of less pressure. And so those walls can actually form a barrier and water can pool under the ground on one side of them. So up around Raton, we have a whole bunch of dikes that run northeast, southwest, and the groundwater is always pooled on the northwest side. And the drillers have learned that. And so they go look for a dike and they drill on the northwest side and they always hit water on the northwest side, and the southeast side is always dry. And so being able to figure out little details like that can sometimes give you that little extra edge for figuring out where groundwater resources might be better. Are there any questions at this point about the two maps that we've looked at? Okay.
Oh,
All right.
wait, could I ask real quick?
Yeah.
What about, so how do fault lines play into with those last two, with proximity to fault lines, if you were to dig a well or drill a well rather? What do you want to consider in terms of, in terms of that?
So faults.
So a dike being a sort of fault line.
Say that again, Joshua?
I mean, is a dike being a sort of fault line? Is that correct?
No, a dike is magma that has cooled and crystallized in a vertical orientation. It may have taken advantage of an old fault plane, and that magma came up the fault plane and crystallized along it. Absolutely. It's taking advantage of any zone of weakness in the rock that it can find to get up. So sometimes it's a fault zone, sometimes it's just fracture networks that wouldn't truly be considered a fault zone. Faults can be either good or bad. They're one way or the other. In the case where it's, for example, magma comes up along it, it's a wall, it's a barrier. Okay, water's going to pool on it, but it's not going to either transmit through it. Sometimes that water will well up along that now barricaded fault zone, but sometimes it just stays pooled there. If we don't have igneous rocks in the mix, if we're just dealing with normal fault planes, there's two different ways they can operate. One is, as that fault breaks and moves, it's crumbling the rocks as it breaks. And because it's crumbling all that stuff during that breaking process, this is now really porous and permeable, and water's going to want to travel up along that fault zone. So in your case, the dry lake springs, those are along a fault zone. That's water that's coming along, it's hitting that fault zone, and it's so nice and porous and permeable that groundwater just goes right up to the surface. And so a lot of spring locations can be oriented along fault planes. But sometimes what happens is, as that groundwater moves along that fault plane, it precipitates out calcium carbonate or silica or other minerals that are in that water. And over time, they gum up that fault plane. And then the fault plane actually goes back to being a barrier to flow because it's basically cemented shut. And we saw this on that very first quadrangle we looked at the very beginning of this, the Singer Lake quad. We saw fault planes that were so cemented that as the limestone weathered down around them, there was just this wall of calcite sticking straight up in the air because it had cemented completely shut from all the calcite. And so water just gets stuck and it can't travel along that fault zone. But Joshua, where I think you're going with this, maybe thinking about fault zones not only as a way for water to come up, but as a way for water to potentially go down. Okay, so when we think about targeted recharge, are we going to want to think about how those fault planes are operating? Are they a barrier to flow, or are they a conduit to flow? Yeah, that's a great question.
Thank you.
Anything else? All right. So this is our very schematic sort of technical, not technical, idea of what we think the world looks like under Northeast New Mexico. And it's a mess. Okay, and this doesn't even have the volcanoes in it. So we have red beds that are folded. We have sandstone that varies in thickness. So sometimes there's no sandstone, sometimes there's 100 feet of sandstone. We have the Morrison with all its different rock types. So if you can get one of these sandstones, awesome. But half the time you're going to hit this mudstone, not going to give you anything. We have Ogallala fossil valleys carved down into the Dakota. So in some places we have the Ogallala at 300 to 500 gallons a minute, sitting a quarter mile away from the Dakota, 5 gallons a minute. Okay, this is a common complaint we see south of Clayton. Well, this well over here, I can run a center pivot on it, but I scoot literally 500 feet that way and I get 2 gallons a minute. Okay, here's our farmland where we can run a center pivot with 300 to 500 gallons a minute. Here's our rangeland where we only have 5 gallons a minute, 10 gallons a minute. Okay, so that comment I made back at the beginning about how agricultural production is tied to the geology, your center pivot irrigation is sitting over the areas where you have the thickest valleys full of Ogallala sand and gravel that can give you 300, 500, back in the day, 1,000 gallons a minute. Everyone else who's ranching, because we don't have the water for farming, is because you're drawing from all these other aquifer units that simply cannot give you that much water. And even that's complicated. All right. And just quickly, this is the big picture geologic map for Northeast New Mexico. So hopefully now this starts to make a little more sense to you. I recognize we just tried to cram 3 years of geology into a little over an hour. But we have the browns and grays of the Precambrian granite and the Sangre de Cristos with old limestone capping that. Here's the orange of the Ocate volcanic field. Here's our Raton Capulan Clayton volcanic field over here. The pale orange is Ogallala, but be careful. Just because there's Ogallala shown on the map, does this tell you how thick it is? There's no thickness here that you can interpret just by what's on this map. Over here north of Roy, the Ogallala is literally a foot thick. So if you're thinking, I'm going to go up there and farm because there's Ogallala, there should be plenty of water there. You've got literally about a foot of it before you're into the Dakota Sandstone. The farming we have is over here, south of Clayton, north of Clayton, down towards Tucumcari. Those big bowls of Ogallala, they go away as we come to the west. And almost all the rest of this is sandstone, limestone, shale that we're dealing with, like we've just talked about. And here's the Turkey Mountains. And this is wrong. That is not the Santa Rosa Sandstone. It's the Glorieta. That's what we learned. One of the things that we learned. So, okay, so quickly, because I know everybody's getting tired, it's past beer 30. When we think about combining all this incredible amount of knowledge, so we have our shallow aquifers. Okay, this is something I know that Joshua and Keisha, we've talked about a lot for Fort Union, is when we think about these shallow alluvial aquifers, is there some way that we can be helping these things to recharge when we do get water? And then for our deeper bedrock aquifers, it's harder for them to accept water because they're tighter, they're cemented, they're compacted. But are there ways that we can get at fracture zones, faulting, and other means of potentially either slowing the discharge of water out of them, or maybe to help them to recharge down the road? This is still a very open question. There's a lot of research needs to be done. Most of these other rock units, they could be good wells, but for a lot of them, those rock units are 200, 300, 500, 1,000 feet below the ground. So as we start potentially having to drill deeper, do those rock units have water in them at 800 feet down? And is that water even drinkable? A lot of times the longer water spends under the ground, the worse the quality gets. There's a well up by Maxwell that is quite literally radioactive. Okay, so they drilled a 1,200 foot well and they can't use it because that water is literally hot. It's got radium in it. And so as we grapple with this never-ending drought and with trying to understand where are our other resources and how can we potentially help the resources we have, these are all the kinds of things that we need to be keeping in our minds as we move forward. And lastly, when we think, so just to kind of try to sum all this up, and I know there's a huge amount of information, but when we think about that geologic map and the cross section, okay, that's that three-dimensional interpretation of all the rock units, both water bearing and non-water bearing, and how we think that they're distributed under the ground. So rather than just punch holes until we find water, can we be a little better about being strategic about where we drill, given how expensive it is to drill water wells? And can we understand why the well over there, a quarter mile away, behaves really differently from this other well? Okay, this is all linked explicitly to this 3D distribution. And then when we add in all that data we collect on your wells every year, the static water level measurements, the isotopic information, tritium, carbon-14, stable isotope, the chemistry, that's giving us how that aquifer is behaving through time. So now we have the 3D, the volume, the shape of our aquifer, and now we add the fourth dimension being time. Now we're also seeing how that aquifer is behaving through time. So the geologic maps plus all this other data that we come in and take at your wells, hopefully now y'all can kind of see what my team's trying to do when we're putting all this together to get that entire picture. The geologic maps are the context. They're what helps us interpret your water table behavior, your isotopic data, your chemical data. All of that comes from those maps. And I think I have one point hidden below everybody. No, I don't. Okay, so this really could have been broken into about like 4 more hour-long presentations, but I hope that that was a good overview of how geologic maps work, how we make them, and why we spend the time to do them, because it takes about 3 years from start to finish to get a quadrangle from drafted to fully digitized. So it's not a small endeavor to do a quadrangle, remembering that's 56 square miles. And so I hope that this gives you all an idea of why we do what we do and some of the information that you can gain as you learn to read and interpret geologic maps. So I'm going to call it there.
Kate, that was great. Thank you so much.
All right, questions, comments, concerns?
Are we going to have access to this PDF, Kate, to refer back to? It's so impressive. Thank you so much. But yeah,
it's being recorded. And so Katie and or Amy will make sure that how you can access it will be shared with everybody afterwards.
Yep.
Absolutely.
And
sorry, Katie.
That's okay. We will definitely share the recording with everybody. And Kate, is it possible to just share a PDF of the PowerPoint as well? If people want to go back to that. Great.
Yeah.
We'll send both out.
Thank you.
Yeah, absolutely.
So just a quick question, Amy or Katie, could we, every one of our well participants ought to see this, right, Kate?
Oh, for the
Harding County. Yeah.
for Harding. Yeah.
I'm thinking maybe instead of making them pay money, I might make them watch this video. Then they'd understand why it's important.
Yeah, absolutely. You can certainly share it around, Sally.
Okay. I think that would be a good thing to do. I think people would really appreciate it. Producers would.
Yeah, and we'll put it on the Alliance's website as well.
Yeah.
All right. Thank you.
I was gonna ask if you had like GIS layers available, or are they more just like still photographs?
So for all of the geologic maps that we've done for our company, the vast majority of those are proprietary. And so we do not share the shapefiles without the explicit permission of either the Soil and Water Conservation District or the landowner for whom the map has been made. But that big, all the open file maps through the state survey, if you go to the New Mexico or Google the New Mexico Bureau of Geology, any quadrangle that has been mapped in the state of New Mexico and has been digitized, you can go through all their maps and you can find the shape files that you need for those maps.
Okay, thank you.
Mm-hmm.
Any last questions? thank you everybody for joining us tonight. Really appreciate it. Kate, thank you so much for your time as well. This was terrific. That was a super informative presentation.
Yeah, thanks everybody for making the time. I know it's a busy time of year and it's late in the day, so I really appreciate everybody making the time.
And I also want to say a big thanks to Amy at NMSU for manning the Zoom controls for us. That was incredibly helpful since I haven't had much experience with it. And also just one more shout out to Sarah and NMSU for all their support. Thanks everybody.